Welcome back, students, to second week of mandatory school learning, also called like for real learning. You can't just call it mandatory. It makes it sound like it's just a test to do. And I'm just so proud of all of you that worked so hard last week to really push yourself to understand this stuff. You came up with some great work, especially work I was able to review on your PHET simulation worksheet. It seems like a lot of you are really digging in because you understand what you're talking about at this point, which is great. This week will be a minor shift from energy. We're going to be shifting into waves, which are how two specific forms of energy propagate, or basically how they move. And if you already guessed, that's sound and light energy. Sound and light energy both move as waves. So before we really dig into sound and light energy, we have to understand what waves are. In order to understand what waves are, we had to understand what energy is. That's why if you haven't gotten a chance to take a look at last week's work, maybe just look at the first video, actually really the second video on the forms of energy and types of energy would be very, very helpful so that you understand where we're coming from. Otherwise, you might be a little bit lost this week. Okay, so like I said, we'll start just by taking a look at the work that you had to do this week, then we'll get into this. It should be a shorter video, and I say that every time, but you know. Okay, so looking on Google Classroom right now, we have this week's office hours changed a little bit. I was going to have it that we were going to have a different schedule this week from last week, but then I realized that the Infinite Campus wasn't matched up with the schedule that Miss J and I had arranged on. So this week it'll look like this. Basically, follow the schedule that you have online from Class Dojo. I'll also post it in the weekly update. Basically 7:04, 5, and 6 you're scheduled for Monday, Wednesday, and Friday, and 7:01 through 7:03 for Tuesday and Thursday. But basically we're going to have Friday as anybody wants to come out and ask questions on that day, you can. Last week we didn't have as many people, but it doesn't mean that, you know, if you were, say, in those other sections that weren't typically meeting that day, that would be the day that you at least know what you don't know at that point. So all that to say, just pay attention to the schedule that we have here. And in the weekly update, I haven't posted the assignments just yet because I need to have these videos done before I do that. But you'll have, once again, 3 video lessons this week on waves. The first one will be on the nature of waves, which is this one. Property of waves will be the second one, and then wave interactions is the third one. I'm going to recommend this week that you actually do all 3 of those video lessons first, and then move on to eScience. For eScience this week, you will be picking your own. So if you get done with the first 3 lessons, you've done the exit tickets for those things, then the next thing to do would be to take a look at those scores, think about the concepts from each of those, and whichever one you feel the most fuzzy about. I posted 3 assignments on eScience, so they relate to these 3 different videos. So if you bombed out on the exit ticket on the first one because you just really don't understand it, then I recommend that you use that eScience lesson that relates to that. That'll be the first eScience lesson, so on and so forth. Then finally, the 5th assignment for the week is another PHET simulation worksheet. So go ahead and do that just like last week. It was a pleasure to get on there and read all your very well thought out comments. Just encourage you always to use proper grammar, full sentences, and if it's asking for you to provide evidence, you know, you get out of that what you put into it. So take the time to really think about evidence, if it's supporting evidence or if it's just, don't give me one of these, I did the work, so check the simulation, that's my evidence. It's like, what did you find out from the information from the simulation? That's the idea. You know better. And if you haven't already read any of this other information, if you're just getting into online learning now because you weren't able to last week, just recommend, you know, read this information down here, read the frequently asked questions, and email me if you ever have any questions. All right then, so let's get started into the actual lesson today. In your Google Classroom post, you're going to find the guided notes for waves. We are working on the nature of waves guided notes right now. Once again, these little doohickeys here, if you just want to type your name in here, say I'm Ming Guan from 703, and I'm doing this on Monday. This is more for your own records. And any blue boxes, this is where it's like a short response, so a couple sentences maybe. And then anything here is where you are supposed to be filling it out. Sometimes it's longer words, but usually it's just 1 word per blank box. Okay, so you should be working in this one if you're on this video, and let's get started. So the objective of this is to understand the properties of waves and the wave-like property of energy in earthquakes, light, and sound. That's like the general unit objective. But today, the specific objective is define and compare the types of waves in order to understand and describe the characteristics of sound and light energy. So we're going to find out that there's a couple different ways that you can categorize light and sound energy, or the waves really. You can look at it just like we looked at galaxies before, by their shape or their age or this or that. We're going to find out how we actually categorize waves today and what that tells us about them. So first of all, like, these are the two questions: what is a wave, and how does energy move in waves? It's interesting to think of that. So this is the first part of your guided notes now, and if you're going into them, I'm going to actually ask you pause the video and literally go ask a couple people in your family, just like we're always asking, well, what is force, or what is energy in the first place? Today's question is, what is a wave and where do they come from? So go ahead and pause. Okay, now I'm hoping that you just came back from talking to people in your family or whoever you can nag around the house. I'm literally going to ask my wife right now, who I think is sitting in the room. You should be able to see her. All right, so my wife's an English teacher. She's working nonstop, just like me. Not really. She works much harder than I do. So, honey, my question is, what is a wave? And where do they come from? I did not prepare her for this, obviously. She kept asking me, what are you going to ask me? I said, I'm going to tell you later.
A wave, something that moves, gives an emotion, maybe from one direction to another. I don't know where it comes from. I think it just exists.
Okay. You heard it from her. All right, I'm going to pause the video right now and actually move locations. Okay, so we just asked that question. Now, whatever your response, hopefully you've written that down in your guided notes. Those things are recommended. They're not going to get graded, but it's still your notes to take with you, and you'll always have them. All right, so what is a wave? A wave is basically, and my wife Jennifer was pretty close to that, it's basically a disturbance that transfers energy through matter or space, right? Perfect. It's honestly, a lot of us know what a wave is, but we don't know the proper description for it in physics. That's fine. That's what we're here to learn right now. But a couple important points here. It's a disturbance. It's energy, and it's traveling through matter or space. Basically, the wave is energy that's passing. It's basically energy in motion. It doesn't always look like this up and down motion, even though a lot of times people think of waves like that, or the kind of wave that you have at a baseball stadium or soccer stadium where everybody's flapping up and down. We kind of understand what that wave looks like that, but there's actually waves that look very different than that as well. It's any kind of a disturbance that's passing in a regular repeated motion through matter or space. They're caused by vibrations, basically forces that cause vibrations. If you've ever seen anybody that's pushed up and down on a rope before, you can't just go up and create a wave. You actually have to go up and down. Now you can go all the way up and down again, just like on this this picture right here, and it creates a vibration. Basically, a vibration would be a back and forth motion, or a forward and backwards motion, back to where it came from, to be considered a full vibration. So basically, anything that does that kind of a regular repeated motion, even if you think about kind of like what a pendulum looks like, that's why I used that demonstration example last week, you basically get a wave. That's what a vibration does. Some of those waves will be smooth, some will be rigid, some will look really pretty, like when you have a droplet falling into a pool of water. Some will literally look like light, even though you don't recognize the wave of it. The wave is what's hitting your eyes to create the sensation of light. On here, like I said, movies, they're basically just moving energy. They move in one direction, and it's not the matter itself that's passing along. It's energy that's moving through the matter itself, which is kind of weird. Sometimes the energy moves through nothing at all, but the important point here is that there's energy that is moving. If you think about waves in a pool, the water will go up and down, but the water is actually not moving in that direction. The energy moves in this direction. And in the process of the energy moving along that pathway, it's going to cause the materials that are in the pathway to move up and down. But just a quick toss back to work and energy. If this object goes up and then it goes down and it comes right back to where it was before, there's actually no work that's been done to it, because the potential energy that you put into it to get the kinetic energy you put into it to move it up just builds up its potential energy, right? And then that potential energy comes back down again, and maybe it's down here, and it'll go back up. At the end of the day, if you drop a pebble into a pond and the ripple goes up and down, but it gets back to where it was, it's not like that ripple itself moved. The water didn't move. It was the energy that moved through the water. And that's one of the indications why it's the energy that's moving, not the matter. And that can happen because if you end up coming right back to where you started from, you technically didn't put any energy into the water. And going off of the conservation of energy law, it's not like the energy disappears. So it has to go somewhere. That's what a wave is. One more look at this, since it's kind of hard to think about that. Imagine there's a duck sitting on a pond, or on a pond, and there's a little bit of wind. The wind gives some energy to the water, right? It's a vibration that causes the water to move this way. Now the wave itself, it might look like the water is pushing, like there's a big hump of water here and it goes underneath the duck, right underneath the duck, on the other side of the duck over here. But actually the water itself is just going up and down. And so that's the interesting part of how these waves are moving. It's the energy that actually, right now there's more energy underneath the duck pushing the water up, and right now there's actually less energy on the duck, so the duck pushes the water away, and then eventually go back to where it started from. So in other words, if the wave and the water wave and the duck himself represent matter, right? Just like water, the duck is just going up and down, and it's actually not moving side to side. The energy is passing through it. So if the energy is moving through something, it is called a medium. Basically, a medium is anything that something is in. So if you say you're an artist and you're painting on a medium, you'll be painting on canvas or paper. There's news mediums, but when we say mediums, we actually say media. That's where you get the news media. It's just a place where it is. So when when energy travels through matter, it's really important to know what that matter is made of, because that medium, basically what that matter is made of, will determine how that wave moves, or even doesn't move. Some waves have to move through a medium, some waves don't. So real quick, I'm going to check on the time here on this lesson. We got 2 minutes left. Oh boy. So we're going to talk about how are waves classified then. So characteristics of waves. You really have a couple different ways of characterizing waves, and we'll take a look at these a little bit more. But based on their characteristics, like their crests and troughs, this would be a transverse wave, say. The shape it takes, basically, and the characteristics that it has because of that shape is one way to classify it. So say the first type of wave that we'll classify based on its characteristics, on its shape in other words, are transverse waves. Transverse waves are these waves in which the particle vibrates in an up and down motion. Light works this way. It's pretty important to know. Here's a video of a slinky. If you can't see it on here, I'd recommend you go into the actual slides presentation itself. You notice the person puts their hand up and down on the slinky, and that energy just passes along. It's pretty weird to think that up and down motion creates a energy path perpendicular to that, but that's the way it works. Transverse waves, we'll take a look at the different properties of these things. All these different things are called the properties of it, and they're all very important for understanding what that wave is going to do when it interacts with other matter.